This is a video about satellite observation of El Nino. El Nino is a recurring weather phenomenon that occurs in the equatorial region of the Pacific Ocean. In a normal year, there is a high amount of convection in the west, which is connected to a high amount of rainfall. The uprising air flows eastward and descends over the East Pacific. This descending air is transported westward by easterly trade winds. These winds interact with the sea surface, and an easterly current pushes the warm surface water westward. The deficit of water in the east is balanced through deeper and colder water. This process is called upwelling. Now, every 2 to 7 years, this circulation pattern changes and an El Nino event takes place. Now, the easterly trade winds are weakened, and less water is pushed westward. So less upwelling occurs at the east coast. This allows warm water to spread eastward. And also the main area of convection shifts eastward and brings extensive rainfalls to the east coast. These El Nino conditions usually persist for a year, and they have several impacts on the environment, like droughts in the west and floods in the east. There's also a huge negative impact on the fishing industry along the coast of South America, because less nutrients reach the surface. El Nino affects the whole globe. For example, the USA, who have to cope with extreme warm conditions in the north and floods in the south during an El Nino year. Because of these huge impacts, it is essential to know more about the El Nino events in order to be able to predict their intensities and potential effects. This is where satellite observation comes in. During the last decades, satellites have observed our oceans and helped us determine more about El Nino. I will address the two variables, sea surface temperature and sea surface height, that can be measured from space and then be related to El Nino. At first, I'll talk about the sea surface temperature. It can be measured by the advanced very high resolution radiometer. This is part of the more recent NOAA satellites, like the NOAA-19. The AVHHR measures reflected visible and near-infrared energy, and also the radiated thermal energy. This is important for our sea surface temperature measurements. There are two channels that measure in the thermal spectrum at different wavelengths. This is referred to as the split window technique, and allows to calculate the transmissivity through the atmosphere, and thus gives us the sea surface temperature of the measured surface. The second variable I'll mention is the sea surface height. This can be measured by a radar altimeter, which measures the distance between the sea surface and the satellite, and can thus calculate the sea surface height. This sea surface height is important to calculate patterns of ocean currents, and also tells us something about the amount of warm water. Satellites with these radar altimeters are, for example, the Topex Poseidon satellite and more recently Jason 2 and 3 satellites. They can make precise observations of the sea level by measuring the time a signal needs to return to the satellite. The radar altimeter sends out two different wavelengths to correct measurement errors, and the satellites also have a microwave radiometer, which simultaneously measures the water vapor concentration in the atmosphere and can thus correct for the influence. Now I'll tell you something about key examples of data. First, I'll mention the study of Song and others, which use AVHRR data in their study to develop an index that groups El Nino events in 5 subgroups. They look at sea surface temperatures over 4 different Nino regions, the region 1 and 2, 3, 3.4 and 4, and then use the data to group events in one of the 5 categories. For example, the most extreme El Nino event of the 20th century, the 1997-98 El Nino, is classified as a strong Eastern Pacific El Nino. It's Eastern Pacific because the longest duration of 17 months was in the Nino 1 and 2 region, and the sum of the regions 1 and 2 and 3 is higher than the sum of the regions 3.4 and 4. The regions 3.4 and 4 refer to Central and Western Pacific. The event is also referred to as strong because positive sea surface temperature anomalies were found in all 4 regions. Other than that, Song and others also looked at the different development patterns, and for the El Nino in 1997 and 98, it started in the Central Pacific, then developed further as a mixed El Nino, and eventually ended up in the Eastern Pacific. At the moment, the NASA uses data of sea surface height anomalies to compare the current El Nino with the one from 1997 and 98. The data were retrieved from Tropics and Poseidon in 1997 and 8, and now from Jason 2 in 2015 and 16. By comparing the two events, it becomes clear how similar they are, and predictions can be made about possible effects and the duration of the event. The comparison will also help predict future extreme El Nino events. To conclude, I'd like to say something about the impact of the human-induced climate change on El Nino. Please bear in mind that the models that predict that future development differ greatly, and I will refer to the study of Kai and others, where the climate modeling evidence shows that a doubling of these extreme El Nino events, like the ones from 1997, 98, and the recent one, are likely to occur in the near future. This highlights the urge to get an even better understanding of El Nino than the one we already have, in order to make more precise predictions for the onset and the possible development of future El Nino events. The current El Nino can be seen as a good opportunity to gain more data for future research, which might enable general predictions in the future.